We have a question here, question 7. It says in the circuit below, the battery has an EMF of 24 volts and an internal resistance of 0.6 ohms. The heater has a resistance of 10 ohms and the fixed resistor has a resistance of 30 ohms. The variable resistor R can change between 0 ohm and 15 ohms, right? So remember, variable resistor, we sometimes call it a rheostat. So this is a resistor whereby we can choose to have our own resistance. We set the resistance to whatever a resistance that we desire, right? And then they say this, with this rheostat or variable resistor, we can change the resistance between 0 to 15 ohms. So we are given the interval here in which it allows us to change the resistance, right? So we can only change between 0 to 15 ohms. Then 7.1, it says the variable resistor R is set at a resistance of 3.5 ohms. So the variable resistor we are talking about is this one with this symbol here. So this is 3.5 ohms. And then in 7.1.1, we are told to calculate the total resistance of the circuit, including also the resistance of the battery, which we know this one to be the internal resistance, right? So internal resistance is the one that is indicated by the small r, which is this one here, 0.6 ohms. But then before we calculate the total resistance, let's first observe this diagram here. From this diagram, we can see that the heater is connected in parallel to this 30 ohm resistor. We are not told here, but then looking at the diagram, we can see that these two are in parallel, right? Because if you can check here, when current is flowing, at this point, what does the current do? It starts to choose a multiple pathways. So it has multiple pathways. When it comes here, it can flow in that direction or it can flow down here. So this is now a parallel connection because now current has more than one pathway to flow. So these are connected in parallel and this one is connected in series, right? So you can see with this one, after here, the current flows, and then after here, there's only one pathway for current to flow, right? So this one is connected in series. Okay, then to answer that, the total resistance of the circuit, including the battery, we will say, let's first calculate the total resistance in parallel connection. So we have 1 over Rp is equals to 1 over R1 plus 1 over R2. So that's the formula to calculate the resistance in parallel. So for R1, we have this 10 here. And then for R2, we have 30. And then punching that in your calculator, you will have 1 over Rp is equals to 2 over 15. But then you will remember that we are not looking for 1 over Rp, we are looking for Rp. So at this point, we have to do our inverse. And then now we will have 15 over 2. So the denominator becomes numerator, denominator. So the Rp is now equals to 7.5 ohms, right? So now this is the resistance of the parallel. But then remember, in order to get the total resistance, we must then take this resistance of the parallel, add it to the resistance in series. But then they said including the battery, so we must also add the internal resistance. So to get the R total, that's Rp plus resistance in series plus the internal resistance. So we have 7.5 plus 3.5 plus 0.6, which adding that will give us 11.6 ohms, right? So we have our 5 marks just like that. Then 7.1.2 says the current measured by ammeter A2. What is the current measured by ammeter A2? First, let's observe current ammeter A2 is connected in series to the heater. So what does this tell us about ammeter A2? Ammeter A2 is only reading the current, so only reads the current of the heat. Only reads the current of the heat, right? So now, in order to find that, we can see that there will be a bit of a challenge because we don't even have the the voltage for the heater, right? So in order to calculate the current, we will need to have the voltage of the heater, and then we can calculate the current. But then note something here. We can see that the heater is connected in parallel, right? What do we know about parallel resistors? We know one thing for sure, that when it comes to parallel resistors, the voltage is the same throughout. So we say voltage is the same throughout for parallel resistors. And then what is divided here? Remember, parallel connection resistors, we know them as current dividers. That is to say, current is divided amongst the resistors. So current is divided amongst the resistors. But when we say divided, we are not saying it is in equal proportion. It is based on the proportion of the resistance. So the one with the higher resistance, according to this formula here, the one with the higher resistance will have to have a lower current running, right? And then the one with the with a lower resistance has to have a higher current, because resistance and current is inversely proportional. So here we say current is divided amongst the resistors connected in parallel. So now, having that knowledge, what can we do? We can first start by calculating the current here. This is the total current. So we know if the ammeter is connected just close to the battery here, we know that it reads the total current. So it reads the total current, but also it reads the current of the one connected in series. Remember, the one connected in series will now experience this whole current, because here it is not it does not have to share anything with any other resistor. In fact, if our resistors are connected in series, we know that the current is the same throughout. So we know that the current that we are going to find in A1 is actually the current that flows in this variable resistor. So now, how can we find that one? We can simply use the fact that we are given the EMF here, and then we are also given the internal resistance, and we do know the total resistance. Remember, this total resistance is the external resistance plus the resistance of the internal resistance, or the resistance of the battery. So EMF, so to answer 7.1.2, we'll say EMF, and then we make use of this formula I, and then R plus small r. Then the EMF, we are told that it is 24, and then now we are calculating the current. But remember, the external resistance plus the internal resistance all amount to 11.6, right? So that's 11.6, and then let's divide by 11.6 both sides. So we have 11.6, and then that will give us a current of 2.07 amperes, right? So we have a current of 2.07 amperes. Now, what are we going to do with this current? We know that this current is here, right? But then remember what we just said about parallel resistors. We said parallel resistors, the current is divided amongst the resistors. Which current is actually being divided here? The current that is being divided is this total current. So we are saying in the parallel connection, this 2.07 amperes will be shared amongst these resistors that are connected in parallel. So this heater will take a certain portion of this 2.7 amperes, and this fixed resistor here will also take a certain portion from this 2.07 amperes. But then remember, the way in which they share is in accordance to this relationship. So the one with the bigger resistance will have to have a smaller current, and the one with a lower resistance will have to have a bigger current. So now, if we have to look at this in terms of ratios, we can simply say, okay, so let me try to erase here. So we can simply say here, in terms of ratios, we can say the ratio to this resistor and this resistor here, that's 10 ohm to 30 ohm. So if we divide both sides here by the smallest number, 10, so we find that the ratio is 1:3, right? So that means for every 1 ohm of resistance, here we actually have 3 ohms of resistance. So that's 1:3. Then we can simply use this relationship here in order to find the current. How so? Let's first start by finding the total sum of the resistance, right? The total sum of the ratios. So the total sum of the ratios will be 1 plus 3, which will give us 4, right? So now, seeing this relationship here, that if one has a bigger resistance, then it must have a lower current. Now, we do understand that if we are to look at this way, that means the 10 ohm resistor will actually have 3/4, which is 3/4 of the current, of the total current. And then the 30 ohm should actually have 1/4 of the total current, right? So the 10 ohm will have a bigger current, so that's 3/4 of the current. But the bigger one, the bigger resistance, will have a lower current. That's a 1/4 of the total resistance. So that's how you do it. After finding the ratios, you simply add the two ratios to find the total of the ratios, and then try to inverse this, right? So the one for the one that is 10 ohm, it will take this 3/4, and the one that is 30 ohm, it will take the 1/4. I hope it makes sense, right? So we have the 10 ohm taking the 10 ohm taking the 3/4, and the 30 ohm taking the 1/4. So now what are we looking for? We are looking for the one for ammeter A2. And then the ammeter A2, we said that this one reads the current of the 10 ohm resistor. So if it reads the current of the 10 ohm resistor, that means we are to go with this one, right? So which is 3/4 of the total current. So how are we going to calculate that? Let's calculate here. Okay. So for the 10 ohm, to calculate the current in the 10 ohm, or rather to calculate A2, we need to say 3/4 times the total current, which is 3/4 times 2.07, because remember, we actually found the total current here to be 2.07 amperes. So when we do that, we find that the current is actually 1.55 amperes. So this is the reading on A2, right? So hope that makes sense. Then let's get to 7.2. It says the variable resistor is now adjusted to have an even higher resistance value. So they say, how will this affect the power dissipated by the heat? Right only increases, decreases, or remain the same? Explain the answer by making use of a suitable equation. Okay. Now, to answer this one, we do understand that here we only had 3.5 ohms, right? But then now, what are they saying? They say the variable resistor is now adjusted to have an even higher resistance. So let's say, for argument's sake, they increase this one to have the maximum resistance that it can provide, which is 15 ohms. Now, how will this affect the power? Remember, power is directly linked to a current, right? So we know that power is I squared times R, right? And then let's try to link it to current. We know that there are also other equations for power which are linked to the voltage, right? And then we also have this one which is linked to the voltage and the current, right? And then since we know here, let's check how will this affect the power dissipated by the heat. So let's first explain what the increase in resistance will do. An increase in resistance will simply increase the total resistance. So remember now, we got this one to be 7.5, right? And then firstly, we added it to 3.5, and then we got that certain value. But then now, if we are to say 7.5 plus 15, you can see with the numbers here that this one will obviously be bigger, right, or greater. So number one, we can say increasing R will increase the what? Will increase the total resistance, right? That's number one. But we know, according to this formula, R is equals to V over I, we know that an increase in resistance actually leads to a decrease in current, right? So we can say now, but according to R is equals to V over I, this will lead to what? This will lead to a decrease in current, right? So if the current decreases, if we now have to refer to this equation here, if we now have to refer to this equation, which is the suitable equation in this case because it refers to power. So if we have to refer to this one, if the current has now decreased, what will happen to power? So current is directly proportional to power. So if current decreases, power also has to decrease. So according to P is equals to I squared times R, the power will decrease. So the power dissipated will decrease because current has also decreased, right? So that's your 3 marks. K. So now let's look at another one. We have question 8 here, which says a battery with an internal resistance of 0.10 ohms is connected to the circuit as shown in the sketch below. The 3 light bulbs in the circuit R1, R2, and R3 are all identical with a power rating of 40 watts each. So these 3 resistors are all identical and they have a reading of 40 watts each. 40 watts each. Right. And then 8.1 says define EMF in watts. What is EMF? So we know that EMF is the maximum. So let's define it. We say is the maximum energy provided, the maximum energy provided by a battery per coulomb charge passing through it. So that's EMF. You define it as maximum energy provided by battery per coulomb charge passing through it. Maximum energy provided by battery per coulomb charge passing through it. Right. Then switch S is closed. Now bulb R2 works at optimum condition and the ammeter reads 2 amperes. Right. So it works at optimum condition, meaning at the maximum condition, and then calculate the total resistance of the circuit, right? So to calculate the total resistance of the circuit, remember here total external. So they were specific. That means this one you don't include the internal resistance just like we did on the previous question. This one is just external resistance. So this one is not included. Now, they said all this are what are identical. So now we must calculate the total resistance. How are we going to calculate the total resistance here? Number one, we are only given power here. We are only given power, right? So we have to find a way to change this power into resistance, right? Then we have this formula. Remember, we were also given here that this has a reading of what? Has a reading of 2 amperes, right? S is closed now. Now bulb R3 works at optimum condition and the ammeter reads 2 amperes. We know that if R3 reads 2 amperes, that means even this ammeter here is reading 2 amperes because remember R3 is connected in series, right? So if these are both connected in series, that means they have the same current. Remember, for components connected in series, the current is the same throughout. So we have 2 amperes here. So that means also the total current is what? Is 2 amperes. So, okay, we can simply use this, right, to find the resistance of R3. Since we are told that these bulbs are identical, that means the resistance we are going to find for R3 will be the same resistance for R1 and R2. So we have power is equals to I squared times R. Then the power is 40 and then current is 2. So 2 square and then R. So this will give us 4. So let's say 4 and then R, divide both sides by 4. So the resistance is 10 ohms, right? If the resistance is 10 ohms, that means R3 is 10 ohms, you are 10 ohms, R1, and then R2, you're also 10 ohms. So now we can actually use this to calculate the total resistance. So these ones, again, they're connected in parallel. And then because here you can see that when current reaches here, it is what? It is alternative pathways to flow, right? But then this one is connected in series because there's only one direction for current to flow, right? So we have 6.2.1. Let's start with the ones that are connected in parallel. Oh, yeah. Then it's 1 over 10 plus 1 over 10. So this will give us, so let's just fast forward to the RP. So this will give us 5 ohms. So you know the drill. You first add this one and then inverse, right? So this will give you 5 ohms, right? And then when you have this, you have to remember that to calculate the external resistance, now you have to say RP plus RS, right? Which is now 5 plus 10, right? The 10 here. Then we have 15 ohms, right? So that becomes your external resistance. Awesome, awesome, awesome. Okay, then 6.2.2 says now calculate the EMF of the battery. Calculate the EMF of the battery. So let's clear here. So to calculate the EMF of the battery, we know the formula goes EMF. So we can see that that's if in 3 marks. So EMF is equals to I times R plus the internal resistance. So the R here is for the external resistance and the small r here is for the internal resistance. So we have EMF. The current here is the total current that flows through the circuit. So that's 2 because we deduced that if here it's 2 amperes, also here it's 2 amperes, which this one indicates the total current. Then the R we calculated previously, it's 15. And then add it to the internal resistance, which is 0.1. And then what is our EMF when we punch all this in the calculator? we find that it is 30.2 volts. Nice. K. And then now 8.2.3 says, calculate the energy dissipated by the bulb labeled R3 in 20 minutes, right? So before I speak of energy, let's first solve this one. We know that if we are given our time in minutes, we should convert, right? So we immediately we see minutes, we just say 20 times 60 so that we convert it, right? So this will give us 2 times 6 is 12, so that's 1200 seconds, right? Then we have that. So we know that energy is actually energy, remember, is just a product of power and time, right? So that's energy, that's power multiplied by time. So to calculate energy, we already have power. Did we calculate power? We were given power, right? Remember, we must calculate the energy dissipated by R3, right? R3 is 40 watts. So we have power here is 40, and then our time, we simply substitute the 1200 here. And then to calculate that one, punch that in your calculator, you have 48,000. So that's 48,000 joules. Nice.